work with various people, and I will mention their names as we state the results, right? Okay, so let me start with some basic energy decay in scalar transport, right? So before I get going, let me also add, if you have questions, feel free to interrupt. I think I can hear you so far. Okay, so let's look at the usual advection diffusion equation, right? So think of concentration of a dye in a fluid. As always, U is going to be the velocity field of the fluid, and theta is my concentration of the dye, if you like. Okay, I'm going to assume that U is incompressible, so divergence U equal to 0, and I'm going to normalize so that my concentration of the dye has mean 0, right? So I'll always make that assumption. Kappa is the diffusivity, right? And for simplicity, I always use periodic boundary conditions through this talk. So just work on the torus. All right, so the phenomenon I want to talk about is the following, which has been mentioned a few times already in this conference, right? So there's stirring, and stirring induces this process of mixing, and mixing tends to move energy to high frequencies. Okay, so if mixing moves energy to high frequencies, well, at high frequencies, diffusion works more efficiently, right? So I get damped a little bit faster. What's the balance, right? Can we quantify it, and what can we prove rigorously, right? So in that vein, so here's a first step to quantifying it, right? Let me define a notion called the dissipation time, right? Which says, well, how long should my scalar theta take to lose a constant fraction of its initial energy, right? And every time I say energy, I mean L2 energy over here. Yeah. So or precisely, I'll say, okay, I'm going to allow U to be time dependent, which is why I have this time inhomogeneous thing. As I say, let me start the advection diffusion equation at time s with initial data theta s. Let me run it up to time t, right? How big should t minus s be so that my energy at time t is 1 over e times the energy at time s? Okay. All right. So I call that tau star. That's the dissipation time. It of course depends on the diffusivity kappa. It also depends on the velocity field u, which I've suppressed here. Okay. So now we all know, right, since u is incompressible, I can use the Poincare inequality, just multiply the equation by theta, integrate out, the advection term cancels, Poincare the other term, right? And you get exponential decay, right? The L2 energy decays like e to the minus lambda 1 is less than or equal to e to the minus lambda 1 times kappa times t, where lambda 1 is the principal eigenvalue of Laplacian, right? So this is times the initial data. Yeah, all norms are just L2 norms, right? Okay, so if I have decay like e to the minus lambda 1 kappa t, then, well, the amount of time I need to wait to lose 1 over e times the initial energy is just 1 over kappa times lambda 1. All right. So that's my, in other words, my dissipation time is of order 1 over kappa. So the two phenomena I want to talk about in this talk, one is this notion of enhanced dissipation, which is, can we find flows where the dissipation time is much smaller than 1 over kappa as kappa vanishes? All right. So the next phenomenon I want to talk about is anomalous dissipation, which is, can I find flows for which the dissipation time is order 1 as kappa goes to 0? And let me talk about enhanced dissipation first, and we'll go on to anomalous. oof, is unstable.
I'm hearing you.
You can't hear me.
Well, no, we can, but it kind of comes and goes a little bit.
Right. My, yeah, looks like one of my networks went down. Right. There. It's coming back up. I need a second.
Okay.
Is it better now?
Yes. Yes. Thank you.
Okay. Right. All right. So just let me know if the internet goes bad. Okay. So the first thing I'll talk about in terms of enhanced dissipation is, well, there are certain conditions that guarantee enhanced dissipation, which is one is mixing implies enhanced dissipation, and we can get an explicit ban, right? The second one is, well, what good is enhanced dissipation? A few things we can do is we can use enhanced dissipation to stop singularity formation or phase separation in some cases, and I'll talk briefly about that, okay? And then I'll talk about certain conditions that guarantee anomalous dissipation, and I'll give one example, right? And if I have time after that, I can talk about certain open questions. Okay. So let me start with enhanced dissipation, right? So the first result I know of in this direction is by Konstantin, Kiselev, Rizhik, and Zlatosh in 2008. And they study time independent velocity fields, U, and they prove a result which says you have enhanced dissipation if and only if the operator U dot grad has no eigenfunctions in H1, right? So let me remind you again, enhanced dissipation really tells me my dissipation time is little o of 1 over kappa, right? So this condition that I've boxed is exactly saying kappa times tau star vanishes. That's exactly little o of 1 over kappa, right? So they call such flows relaxation enhancing. It's a nice spectral characterization. Weakly mixing flows have to be relaxation enhancing, but the converse is false. They have an example. And they also don't have information on the rate at which kappa times tau star vanishes, right? There's a reason they don't have information on this, because the basic assumption they make, which is U dot grad having no eigenfunctions, is really weak, right? In order to get information on the rate at which kappa times tau star vanishes, you need something stronger. You need something like the mixing rate, right? So we looked at this along with Yuan Feng, who is now a postdoc at Penn State, right, and myself. So I say, okay, suppose I have the velocity field U, which I assume to be mixing. So mixing in exactly the same sense as we saw in the previous talk of Michele and was mentioned also before, right? So if you're mixing, I just want to look at the inviscid flow, right? So the flow of just the velocity field U with no diffusion, and say if I look at scalars that are transported just by the flow U, they get mixed as time goes along. In what sense, right? Well, we measure the mixing norm using H-1, as was talked about before. Think about this as the mixing scale. And I ask you, well, at time t, what's the mixed scale of your inviscid scalar, theta, right? So the mixed scale is bounded about by your mixing rate, which I'm calling H, times the initial H1 norm, right? And there's this asymmetry between norms, which you really have to deal with when you're dealing with inviscid mixing, because, I mean, otherwise I could take a perfectly unmixed concentration and flow it backward by the flow of U for some time, and then of course, right, I get unmixing, right? So you need to be a bit careful, right? The only way you can define mixing rigorously is this asymmetric norms over here, right? So I have H-1 on the left, my mixing rate H on the right, and then the H+1 norm of the initial data on the right, okay? So this is my a priori assumption. My velocity field U mixes with a certain rate, okay? Then my result is I can give you an explicit formula for the dissipation time, right? Which is I'm telling you that the amount of time I take to lose a fraction of your initial energy is 1 over kappa times capital H of kappa. What's capital H? It's something I can write down in terms of the mixing rate, which is, look at this equation, the mixing rate H of 1 over 2 square root lambda kappa, and solve for that is equal to 1 over 2 lambda. Solve this over lambda. Yeah. Once you solve it, whatever the answer is, that's called H of kappa. So it's easy to see, if you make some reasonable assumptions, that H of kappa has to go to infinity as kappa goes to 0. It's worth writing down, right? H of kappa goes to plus infinity as kappa goes to 0. Yeah, so the bound I've got here for the dissipation time is really much, much smaller than 1 over kappa, because that's that huge constant in the denominator there. Right? It's also good to work in terms of examples. So suppose I concretely told you that my mixing rate was exponential, right? And as we know, exponential is the fastest you can mix, right? So suppose I am exponentially mixing. Then if I solve this equation here, what do I get for tau star? I get log of kappa square. Okay. There's also the result by Michele, Tarek, and Delgadino that says exactly the same thing, right? If you're exponentially mixing, then your dissipation time is of order log kappa square, right? And just to like belabor this one extra second, what does this mean? If I plug this back into the advection diffusion equation, it's telling you that if I look at the advection diffusion equation, right, the energy, the L2 energy decays like e to the minus, not kappa times t, it's e to the minus t divided by log kappa square, much, much faster than before, right? And of course, this square over here is a bit unsettling. I believe it's false, but it's the best we can prove, right? I really believe that the optimal time should be log kappa. I have some intuition about this, but I cannot prove it. Okay. My apologies, keep switching in the wrong direction. So let me, rather than go into the proof of that, let me briefly talk about some applications, right? So here's the Keller-Siegel equation, right? Which is what I'm not going to do is I'm going to use this notion of enhanced dissipation to prevent blow up in the Keller-Siegel equation. So let me introduce that quickly. So I'm going to think of rho as the population density of bacteria, and look at the equation. dt rho minus Laplace rho is equal to chi, which is a sensitivity parameter, times the divergence of rho gradient Laplace inverse rho minus the average. Okay, so rho bar is just the average on the torus of rho. I'm doing everything with periodic boundary conditions. Why does this equation come up, right? Why do you have this divergence of this term on the right hand side? So the physics is that, okay, the bacteria secretes this thing called a chemoattractant, and then it senses the chemical potential, right? And then the population density of the bacteria evolves with a bias that's directed by the concentration of the chemoattractant, right? So if you write it out, typically you write it out as a coupled system, and then if you just simplify it a bit, you can put it in this form, right? So right hand side has this gradient Laplace inverse and then a divergence nonlinearity. Okay, so this has been introduced, I guess, by Keller and Siegel a while back. There was a mathematical study in the 90s initiated by Jaeger and Lukehaus, which did the following, right? So if my initial density of the bacteria is small, then you have global existence, right? And they exhibited examples where the initial data was large, where you have blow up. And why should you have blow up? Just think about it as follows, right? So if I have a concentration of bacteria, let's say that's the concentration, I have diffusion that's pushing it away, yeah? But as I pointed out, right, there's also this chemoattraction thing, right? It creates a chemical potential. Clearly, the chemical potential is going to have high concentration in this area, right? And it senses this and moves towards the chemical potential. So there is this chemoattraction phenomenon, which is making the bacteria concentrate. So what wins? There's a balance between these two, right? And it's certainly possible in certain situations for the chemoattraction to win and cause a population explosion at one point, right? And that's what they saw exhibited explicitly in this initial paper of Jaeger and Lucas. And of course, it's been studied extensively since. The record now is that if your initial mass is greater than 8 pi, that's necessary and sufficient to have blow up, right? And there's a lot of results on this, starting from Delvaux and Bertham in 2004. Right? Okay, so what can we do, right? So this problem was motivated by an earlier iteration of this conference, right, where I guess Jeff Weiss posed a certain problem and Sasha got interested in it, right? And it led to this result of Sasha Kiselev and Xiao Xu, right? Which is I say, hey, look, I'm going to take the Keller-Segal equation, which I rewrote for you, and I'm going to add to it an advection term. So suppose you just stir the bacteria population, right? Then what happens? So Sasha and Xiao did the following. They exhibited two families of velocity fields, right? Such that you give me any initial concentration. Doesn't matter if the mass is bigger than 8 pi or not, right? Whatever you give me, I can always find a velocity field u from either of these two families, such that if I add advection with the velocity field u, I stop the blow up. Right? Solutions remain globally regular. Right? Then, of course, there were some related results by Bedrosian and He, and then by Seming He, and one by He and Tadmore. Right? Let me not go in that direction, but let me quickly tell you. Right? So the result that we had with Xiao Xu and Andrzej Zlatosz is the following. Right? All I need to stop the blow up in the Keller-Segal equation is to add advection with a small enough dissipation time. Right? So let me be a little bit more explicit on that. Okay. So remember, tau star was the dissipation time, right? Which is, that's the amount of time I need to wait in order for my advection diffusion equation, no nonlinearity, loses a constant fraction, in this case 1 over E of the initial energy. Okay. So since I wrote down the Keller-Segal equation with diffusivity kappa equal to 1, I'm looking at the dissipation time of U over here with kappa equal to 1. And I wrote it in semi-group notation down here. So our theorem says that if you give me a velocity field U with dissipation time tau star that's below some threshold, right? Tau naught. Yeah. Then I have to have global regularity. Right? So no matter how large your initial data was, I can find you a tau naught positive, right? Such that tau star less than tau naught implies global regularity. So how does this work, right? So let me give you a quick sketch of this proof, right? So the way it works is the following. Okay, I'm going to rewrite the Keller-Segal equation in the following form, right? I'm going to write it as the advection diffusion equation, so dt theta plus u dot grad theta minus Laplace theta, and all the nonlinear terms that we take and combine on the right-hand side to be n of theta. Okay, and I'm going to subtract off the mean and pretend that theta is something which has mean 0. So integral theta naught equal to 0. Now, what can I do with this? So the first thing I can do is just a naive calculation with the energy inequality, right? So I can take this equation, multiply it out by theta, the advection term integrates to 0, the theta times Laplace theta, that integrates to our usual norm of gradient theta square. And theta times the nonlinearity, well, okay, this I need to hit with my standard calculus inequalities and control it. So I can control it, and I can control it by, in this case, L2 norm to the 4 plus L2 norm square, right? Plus a little bit of the H1 norm. So, okay, so play with this a little bit and you see the following, right? If what I get from the positive term, so integral of theta Laplace theta on the left, right, which is norm of gradient theta square, beats what I get from the nonlinearity on the right, then the L2 norm decays, right? And this is just like energy estimates directly, right? So I stated that over here, right? And I stated that in the form that it's going to be useful later, which is if, let's work on an interval tau star. If I look at the time average of the H1 norm of theta on the interval tau star, and it's bigger than the contribution I got from the nonlinearity, which is what I have on the right-hand side, right? Then the L2 norm must decrease. Okay. So this is case one. Okay. So suppose now I did not have this above condition, right? Which is, suppose my time average of the H1 norm was below what I got from the nonlinearity. Okay. So now that I'm reading this, there should be a 1 over tau star on the right-hand side. My apologies. Sorry for that typo. Okay. Okay, so now what do we do? So now the idea is that, hey, look, if my H1 norm was small, I'm going to use mixing of the velocity field U. What does mixing do? It generates high gradients, right? If it generates high gradients, eventually it'll make this guy big enough, so it'll help me, right? So this is all good philosophically, but how do I actually do it? Well, the idea is very simple, right? So first, I'm going to write down theta using the Duhamel's formula, right? So if this was the equation that gets the evolution of theta, let me write it in terms of Duhamel, saying theta at time t is initial data times the solution of the linear semigroup plus the nonlinear term, the time convolution you get from Duhamel, right? Then blindly take L2 norm of this right-hand side, right? So, okay, so L2 norm of theta at time tau star is, well, tau star was my dissipation time. Yes, so that's how much time I take to lose some constant fraction of the initial energy. So when I take L2 norm of the first term, I get a constant in front here, which is strictly less than 1. In this case, I got 1 over E. Yeah. And then I got the second term, right? Okay, so this L2 norm, just Minkowski and put the L2 norm inside the integral. So I have integral 0 to tau star of the L2 norm of the nonlinearity. So my aim is to somehow bound the second integral by some constant less than 1 times the initial L2 norm, right? So I show you that the L2 norm doesn't grow, right? And say, well, yes, okay, so the first term I just copied. What do I do with the second term? Again, hit it with calculus inequalities, right? I'm going to write it as tau star times the time average of this nonlinearity. Bound the nonlinearity by, let's say, a little bit times the H1 norm plus the L2 norm to some large power, right? Now, if I've bounded it by something times the H1 norm, hey, look, my assumption was the time average of the H1 norm is already small. Yeah. So whatever I've done in terms of the H1 norm, that's not going to affect anything, right? It's, I mean, by assumption, it's already small. I can ignore that. I have something times the L2 norm. Well, just tinker with this. I have a little bit of room since I already had a constant less than 1 times the L2 norm. Use that room over here times tau star to ensure you get a constant that's strictly less than 1. Yeah. So as long as I make tau star small enough, I can play with these calculus inequalities and guarantee you that the L2 norm does not grow. Now, if your equation has enough structure to say this is enough to stop a blow up, then you stop a blow up. And the careless eagle does, right? So this is a nice general principle that works in a whole bunch of situations. Let me, before I state other situations that it works, let me just point out, right? Hey, look, in order to apply this theorem, I need to produce for you, given any tau naught, I need to produce for you a velocity field with small enough dissipation time. Well, how can I do it? Well, one option would be, suppose I had a mixing velocity field, V, and then I just rescale it, right? So take the mixing velocity field, increase the amplitude and speed up time, right? Then you can just do an immediate calculation from our previous result and say the dissipation time of this guy vanishes as the amplitude goes to infinity. So no matter how small you want me to get, make tau star of u, I can always do it by making A large enough. But the problem with this is examples of mixing flows are hard to construct, right? In fact, as we heard before, right, a smooth time-independent mixing flow on the torus has not yet been done, right? On the 2 torus, of course, smooth time-independent doesn't exist, but on the 3 torus, that's an open question, right? Even time periodic is an open question. Yeah. So since these examples are hard, right, here's another option. Maybe I can use something explicit. How about a cellular flow, which is both strong enough and fine enough, right? And indeed, so we have a theorem in the same paper with Andre and Shao. Let's say if you take a cellular flow, which again to this audience I assume is well known, right? Which is if I just draw you streamlines of the Hamiltonian over here, right? So a cellular flow is something like with Hamiltonian sine x sine y. All I'm doing over here is I'm telling you, well, let's rescale the cellular flow so that the size of the cell is something small and the amplitude is something large, right? Then it works. Why does it work? Okay, so proof takes a little bit, but let me just give you one ingredient that goes in there, right? Which is, there's this notion called the effective diffusivity, which people have studied in the context of cellular flows. And we have a bound that says that, hey, look, I can bound the dissipation time, tau star, in terms of log of the effective diffusivity times the effective diffusivity raised to some power, some negative power. So it's in the denominator over here, right? Exactly as I've stated. And this effective diffusivity has been studied a lot, in fact, starting from Childress, I think, right, in the fluids community, right? So you know exactly the behavior of the effective diffusivity as you do some rescaling, right? So I can always make sure that I can take a cellular flow with strong enough amplitude and small enough cells to make the dissipation time arbitrarily small. Okay, so the proof is a bit technical, so let me not go in that direction. But since Carnegie was mentioned earlier in this conference, right? Let me say a few words about this as well, right? So what's the Carnegie equation? It models phase separation in binary fluids, right? So if I have something with like an alloy, and I cool it below the critical temperature, you see that the phases separate, right? So here are some pictures, right? We start with everything mixed, and then gradually the phases separate, and finally you see these characteristic ridges, right? So what's the equation? This was mentioned before, right? So time derivative of C plus kappa times the bi-Laplacian of C, right? Not one Laplacian, is equal to Laplacian of a nonlinearity, in this case C cubed minus C. Again, you probably noticed if I just expand this nonlinearity, I have minus Laplacian C on the right-hand side, right? So that's Laplacian with the wrong sign. These are growing modes, right? Okay, so again, this equation has been extensively studied, right? What are the equilibria of this equation? Let's call C bar to be the average, right? This average over here, right, is unstable. And then look at the two zeros of the potential, which is plus and minus 1. Those two are two stable equilibria. Right? Mass is preserved, so whatever initial concentration average I start with, that just stays the same, just by integrating this equation, right? And what we typically see is when I put in mean zero data, I see phase separation. So the theorem that we have with Yuan Feng, Yu Feng, who was Jean-Luc's student, right? Me and Jean-Luc, right, is the following. If I take the Carnegie equation and I add strong advection, I can stop the phase separation, which is I converge to the average, the homogeneous spatial average exponentially fast. There's no phase separation, right? So just to spell that out a tiny bit more, right? Let me just state what the theorem is. So first, I'm taking the Carnegie equation that I stated from the previous slide. I'm adding an advection term, u dot grad theta. Yeah. So now you see, since I have Laplacian square instead of Laplacian, I'm going to call the dissipation time to be the dissipation time with Laplacian square instead of Laplacian, right? So, or more generally, let's call tau star alpha to be the dissipation time of the velocity field u with diffusion to be minus Laplace power alpha instead, right? Which is look at the scalar transport equation, right? U dot grad plus minus Laplacian to the alpha, right? And look at the semigroup of that. How long does it take to lose some constant fraction of the initial energy? Okay. So how does our theorem work? It's a little bit different from what we had for Keller-Siegel, right? So in 2 dimensions, it works exactly the same, right? Which is you give me any initial configuration, C naught, right? I can find you a tau naught strictly positive, such that if my dissipation time of with 2 Laplacians of u is below tau naught, then I converge exponentially fast to the homogeneous mean, right? In three dimensions, it becomes a little bit different, right? It's not this result anymore. What I need to make it work is I need the dissipation time of u with 2 Laplacians times the square root of the C1 norm of u to be small, right? If this product is small, then I converge exponentially to the homogeneous state, no phase separation, right? Now, of course, the question is, how can I make flows such that this product, C1 norm raised to half times the dissipation time, is small? Well, it turns out if your velocity field u mixes at a fast enough rate, then this works out. So explicitly, you need the mixing rate of u to be faster than 1 over t. Then you can just rescale it and guarantee that after some rescaling, you can make the C1 norm times the dissipation time vanish, right? But I found this a bit unsatisfactory. So cellular flows, for instance, I could use that effectively for Keller-Siegel equation. Can I use that here? So, well, estimating the dissipation time for cellular flows, now I don't have a comparison principle because it's bi-Laplacian, right? Not the Laplacian. My previous proof didn't work. So I said, okay, why don't we see, can I estimate the dissipation time of a flow with the bi-Laplacian in terms of the dissipation time of the flow with just the standard Laplacian, right? Which is, can I estimate tau star 2 in terms of tau star 1? And if I can, I already know what tau star 1 is for these flows. So maybe I can use that and win, right? So it turns out I can, right? Here's the estimate I get, right? So the dissipation time with the bi-Laplacian is bounded about by the dissipation time with 1 Laplacian, the standard Laplacian, times the C2 norm of the advecting velocity field. Now it looks like you've won here, right? Which is, looks like you've got the estimate you wanted, but this estimate is fantastically bad. If I even plug it into what we had for cellular flows, it doesn't guarantee that you get cellular flows with arbitrarily small dissipation time with the bi-Laplacian. So even something simple like this, I don't know how to do, right? But okay, so let me briefly mention, so there are a few other results which are very nice, which are not by me, right? But let me mention them. So Yu Feng, Bining Hu, and Xiao Shu have some extensions to the P Laplacian. Yuan Feng, Shi and Wang used helical flows for the 3D Komoto-Shevardnadze equation to get similar results. And then of course, Anna has a bunch of work, in fact, 2 papers about doing using dissipation enhancement to stop blow up of the Komoto-Shevardnadze equation. And of course, there are different issues that go there, right? But maybe we'll hear about them later in this conference. Okay. So can I, unfortunately, due to the difference in time zones, I don't know when I'm supposed to stop. Can you let me know how much time I have left?
Yes, you have another 15 minutes or so.
Okay, great. Thank you. So, okay, so in 15 minutes, let me try and give you a flavor of what happens for anomalous dissipation. All right. So, as I said, enhanced dissipation was I lose some fraction of my initial energy in time scales which are strictly smaller than 1 over kappa. Anomalous dissipation is when I lose a fraction of the initial energy in time scales of order 1, right? Or equivalently, if I just look at it through the energy inequality, let's look at kappa times integral 0 to t times norm of gradient theta square, my apologies. This thing should be bounded below by constant chi, right? That's independent of kappa times the initial energy, right? So I want to do this over here. The time that I've taken is capital T, and the constant I've chosen on the right-hand side is chi. Both of them need to be independent of kappa. This is expected in certain turbulent regimes, right? And right. So the main result that I'll talk about is one criteria that guarantees anomalous dissipation and one example satisfying this criteria. Okay. So this is joint work with Tarek El-Gindi, TURW03, and Inji Jeong, right? And since, let me write their names. Travas and Jeong, right? Okay, so the main result is the following, right? So I'm going to take capital psi to be the set of all the pure harmonics, right? Which is either sine x, sine y up to frequencies, or sine mx cos ny, or cos mx sine ny, or cos mx cos my, right? Take the pure harmonics, subtract off the trivial things from this, which is the constant 0 and the constant 1. Okay. So my first theorem is that you give me any alpha between 0 and 1, I can find you an epsilon alpha and a chi alpha strictly bigger than 0, and an explicit velocity field u, which is the following, right? So my velocity field u is smooth before the time capital T. It's integrable in time with values in C alpha. That was the alpha I chose over here. That's the Holder exponent. And it's bounded. Okay. So I can find you this velocity field such that if my initial data is reasonably regular, H2, and is in a cone around these pure harmonics, right? So this condition I've written over here is just pick any psi from the set of all pure harmonics, and I need to be in a cone with the angle epsilon alpha, if you like, around this guy. In that case, I have anomalous dissipation in the following sense. So I look at kappa times integral 0 to t of norm of gradient theta square. It's bounded below by chi alpha that only depends on alpha, right, times the initial L2 norm, the initial H1 norm. Okay. So if your arbitrary initial data in H2, I can still get anomalous dissipation, but in a slightly weaker sense, right? So I can get, so arbitrary H2 data, I can get the same inequality, but the constant chi now depends on the initial data. Okay. And let me just make one quick comment, right, which is, why am I looking at Holder continuous, right? Alpha between 0 and 1. I'm choosing U to be L1 in time with values in C alpha for alpha less than 1. The reason I'm doing this is because if alpha is equal to 1, you can't have anomalous dissipation. If you use L1 in times with values in C1, there's no anomalous dissipation. Right? That's not hard to prove. Okay, so how does this work, right? So just maybe let me briefly tell you what the criteria is, right? So I'm going to look at two things, right? One is the inviscid equation, dt phi plus u dot grad phi equal to 0. Two is the advection diffusion equation, dt theta plus u dot grad theta minus kappa Laplace theta equal to 0 with the same initial data. Okay, my upfront assumption has to be that the integral of the H1 norm square of the inviscid equation has to go to infinity. Okay. And then my second upfront assumption has to be either product of L2 norm times the H2 norm of the inviscid equation is bounded above by the H1 norm square, or alternately, product of the H minus 1 norm and the H plus 1 norm is bounded above by the L2 norm square. If either of these things are satisfied, then you get anomalous dissipation. There's a kappa missing over there. You get anomalous dissipation with an explicit constant on the right-hand side. Okay. And let me just point out, let me just comment on both these assumptions that I'm making over here. Notice this inviscid equation, L2 norm is conserved. Yeah? So L2 norm of phi at time t is L2 norm of phi at time 0. Right? So by interpolation, if I look at the H1 norm square, it's bounded above by the L2 norm times the H2 norm. What I'm assuming is the reverse inequality. Yeah. Same with this guy, right? The L2 norm square is bounded above by H minus 1 times H plus 1. I'm assuming the reverse inequality. In this case, I can get you anomalous dissipation, right? So, okay, so I'm not going to go into the proof in the interest of time, right? The proof is it's pretty elementary. It basically fits on these two slides, right? It's a bit tricky, right? But okay, it works out quickly. There's a nice connection you have to mixing, right? Which let me just briefly state, right? So if you notice, our condition for anomalous dissipation was one of the conditions was this reverse interpolation inequality, right? H minus 1 times H plus 1 is bounded above by L2 square. Okay. Now, if U was exponentially mixing, then I know that the H minus 1 decays exponentially, right? Which is e to the minus some constant times the H plus 1 norm, right? I also know, since it's the implicit transport equation, I also know that the H plus 1 norm grows exponentially. Well, what's one bound of this, right? It can certainly grow by e raised to t times the C1 norm of U, right? That you can just do immediately by Gromboll. But this bound is a bit wasteful, yeah, because C1 norm of U kind of says the growth rate is like the worst case at every point, which is a bit wasteful, right? So you can get other bounds, right? So for instance, I can tell you that the H1 norm grows exponentially if I pay a prefactor that depends on the initial data and only put an L2 norm of U in the exponent. My bad, an H1 norm of U in the exponent, right? Okay, but regardless, I can get upper bounds for the H1 growth. To get the assumption that I need for anomalous dissipation, right, I don't just need any upper bound for the H1 growth. I need a matching upper bound for the H1 growth, right? Which is I need the H minus 1 to decay like e to the minus some constant c times t, and the H plus 1 to grow like e to the same constant c times t, right? I don't know any explicit examples of this, right? So the way we prove our theorem is we construct a flow that gets the H1, H2 balance condition I stated before. The H minus 1, H plus 1, I don't know any examples. If I did have such examples, then I would be able to get enhanced dissipation with an optimal log kappa time scale. And right, I don't know how to do it. Right. So can I confirm how much time do I have left? Am I out?
Have until 12:15, but including questions. So,
okay, so let me just wind up in a few minutes and then we can pause for questions. I guess the basic flows that we had that satisfied the bound were basically shear flows. Which we took the sawtooth numbered, right? Take one in the vertical direction and then take one in the horizontal direction. We have to regularize and then we have to rescale them a bit and suffer somewhat explicitly, right? To show the bound that we want, right? Maybe let me not go in that direction much further in the interest of time. And let me end with something which I learned from Charlie, and I don't know how to do, right? So again, right, I'm very happy to hear what John said at the beginning of this conference. A lot of these problems that I got into was after hearing Charlie's talk on it at some point. I think I heard Charlie speak about this at a conference in 2011 for Peter's birthday in China, right? And shortly after reading Jean-Luc's paper and talking to two of them, right, got me into this area. So really, Charlie had a huge influence in my career. It's unfortunate that he's not here, right? But one thing I learned from him was this lower bound on the advection diffusion equation. So if I look at, if I look for lower bounds, again, so dt theta plus u dot grad theta minus kappa plus theta equals 0. Turns out the best lower bound you can find in the literature is double exponential in time, not single exponential, right? There's this really nice paper by Charlie and his student Miles, his former student Miles, that gives numerics and some intuition saying double exponential decay should not be possible, right? His point, if I understand correctly, is that diffusion and mixing balance as this thing called the Batchelor scale. And after that, you only get single exponential decay. You can't go further. And I actually had a bet about this with Charlie because around the same time, me and Yuan looked at the same thing in discrete time. And here you have an example. I have an explicit example where I do get double exponential decay. I don't know if it's generic, but I have one example. There's a paper of Thifault and Childress in 2003 that says it's probably not generic, right? But okay, there's some work in progress. I had a bet with Charlie saying, hey, I can make this exponential work. I can make this example work in continuous time. But I don't think it's been a few years and I still haven't managed to make it work. I think I can make it work on manifolds which are not the torus. On the torus, I don't know how to do it, right? So maybe not to go too much extra in terms of time. Let me stop here, right, on this note, and I'd be happy to take any questions if you have.
any question or comments from the audience? Yes.
Whoops. So I heard Anna, but I don't hear the question.
You'll hear it now.
Ah,
Okay.
sorry.
Thank you for your very nice talk. Your example with the advective Carnegie equation, you didn't specify where U came from. Does your proof go through if U comes from Navier-Stokes?
Yeah, so it works no matter what. All I need is, as long as U has a small enough dissipation time, then I can give you this thing. Now the problem, if U comes from Navier-Stokes, you need to tell me that U has a small enough dissipation time. Now, if it's just deterministic Navier-Stokes, I have no idea. I don't know if these flows are mixing or not. But if you take the stochastically forced Navier-Stokes, there's a theorem, right, that says that generically you're exponentially mixing. So your amplitude is large enough, you have to be sufficiently mixing, you can get a small enough dissipation time, and you can stop the phase separation.
Of course, in that case, the field C will also affect Navier-Stokes because it's not a passive scalar.
Right. This is a good point. So if you look at the same result, if I look at the coupled Navier-Stokes Carnegie with stochastic forcing, I don't know if you're still going to be mixing as fast or not. That's a good point. So that I don't know.
Thank you.
Right.
Any other? Yes, okay. I have to go around with the microphone, so hold on.
Yeah, no rush. Thank you, Anna.
Hi, Gautam. This is Michele. Actually, I have a question on this slide. So do you have any idea of what should be the right estimate for tau2 in terms of tau1, in terms of dependence on U? Because, I mean, my feeling is that if you're not using anything about U, just some regularity, then, I mean, U could be 0. I mean, okay, maybe there is a 1 there that you haven't put, but okay, there should be a difference of a Poincaré constant between the two times, and that's it, right? If you don't have a
sure, you can put a 1+ and that's okay.
Yeah,
right? Right. That should be okay.
Right. But then, so what should be the dependence on Laplacian of U? What I mean on U, and what is the right dependence that you need for making it work for the cellular flow?
So what I would, I don't know what the right dependence is or what it should be, but I do know what I want. If I could get a power here that's less than 1, I would be happy. Because you see, I mean, just to go back in the condition that we had for the Carnegie 2, right? I had the norm of U raised to C1 norm of U raised to half times the dissipation time. I needed that to be small. If instead of half, I had 1, right? This is a condition that's impossible to satisfy, right? So, I mean, this power 1 is the thing that messes you up in terms of scaling and whatever else you want to do. So I don't mind paying like 10 norms of U, maybe that's okay. But if you can give me a small power, I think I would be happy. But I don't know.
What about just gradient of U?
Gradient of U, I don't know if it's possible.
You wouldn't be happy.
But yeah, if it was just gradient of U to power 1, I would not be happy. It would not help, right? Because even up here, if I had gradient U to power 1, I'm going to get burnt, right?
Okay. All right. Thank you so much.
Yeah.
Is one question from address or comment?
Yeah, I have a question. Is there any, let's say the following, does any of this you think anticipate or expect to work in bounded domains, not periodic boundary condition, any of this?
Yes. I mean, this notion of dissipation enhancing is perfectly general. It works bounded domains just as well as it does in periodic boundary conditions. And the proofs of using the nonlinearity using dissipation enhancing to prevent blow up, like the proof I showed here, this thing just works line by line, right? The catch is you need to find me flows that are dissipation enhancing in bounded domains, right? This is harder. In terms of examples, it's harder to find them, right? There's this example of Tarek and Andre, but unfortunately, it's not regular enough that you can just plug in, right? I need some basic smoothness of you, right? But cellular flows are perfectly fine.
And concerning your dissipation, like the anomaly, so the velocity field, basically you said it's supposed to be some C alpha or something like that, correct?
Yes.
So, I mean, if I understand correctly, the mechanism is basically, if you follow characteristics, you form a shock, and that's why the gradients are large, and therefore gradient times kappa will remain positive. Is this okay? And argument? I mean, hand-waving argument, you form a shock because the characteristics, without the viscosity, the characteristics have to meet. Because you don't have uniqueness.
It's C alpha. So if I just, if you just give me 1 second to scroll. So the regularity condition I have, right, it's smooth before time capital T.
Yeah,
right?
but then what happens at time T? This U is become C alpha, correct?
Right. So at time T, I mean, this flow becomes is crazy, right? Because it's finer and finer scales horizontal, and then finer and finer scales vertical. So at time capital T, probably the characteristics meet, because I mean, this is like crazy.
That's exactly my point. I mean, my point is that because you don't have uniqueness for the ODE, the characteristic meets. Therefore, you have singularity in the gradient without viscosity, and therefore the gradient becomes infinite. And that's why it's expected in that sense that the kappa times the gradient is infinite. That's what happens in burgers.
Yeah.
That's exactly what happens in burgers. I mean, as long as the U is smooth, then there's no shock. You have no dissipation of energy.
Yep.
However, the minute the shocks, forms, then you have this problem. I'm just basically trying to understand it in simple words before start talking about larger, smaller scales. Is this basically what the mechanism that's happening? That's on trying to shed light in that sense.
No, yeah, I think so, right?
Thank you.
I can't guarantee that the characteristics meet, but I think that's what's happening at the end of the day.
Any further comments or questions from the live audience? Anna? No. Okay, so let's thank Gautam then. And for the live audience, we have lunch now, and we'll resume at 1:30 UK time. Thank you, Gautam. Beautiful talk.
Thanks, Anna. See you.